So the Hack computer has got the two types of memory. It's got the first type is instruction memory. So this ROM, or the read-only memory, comes preloaded with a program written in the Hack machine language. So we call it the ROM 32K. So it actually consists of 32K 16-bit registers. So in reality, it's actually got 64 kilobytes of memory space. We know this obviously each 16-bit register has got 2 bytes. So 32K memory for each kind of slot is 2 bytes, will give us 64 kilobytes. And then each register within this memory contains an instruction. So, to read out an instruction, we just supply the 15-bit address for that instruction, and then we can just read the output of the memory, and the instruction will be there. So this is actually a built-in chip, so we don't actually need to implement this. This is kind of provided for us. So at this point, we don't worry how the program is going to be loaded to the ROM. We just use a simulation tool provided as part of the Nanta Tetris suite, and we'll use it to load in an assembled Hack file. But in reality, we have to use a special programmer to write the binary instructions to the flash memory. For example, this is for a microcontroller at least. You'd write the code on a computer, compile the code to get the binary file, and use a programmer then to copy the compiled and assembled file into the microcontroller flash memory. So flash memory isn't actually read-only, because we can, by the fact that when we're programming it, we're obviously writing to this memory, so it's not read-only. But for an actual read-only memory device, so maybe thinking like a cartridge for a games console, the actual binary image is burned in the factory, and it can't be changed after that. Each cartridge has got a fixed set of instructions or a fixed computer game loaded into it, and it can't be changed. And also, some microcontrollers do have an electrically erasable programmable read-only memory, or EEPROM. So we can, store data in a kind of ROM inside of a microcontroller sometimes, but it's typically just a few kilobytes of memory that can be used for storing passwords and so on. It's because one of the main things of ROM is that, or flash memory, is that it's non-volatile. So when we turn the power off, the contents of the memory are preserved. Now for the data memory, which is essentially the RAM chip, to read from that memory, so we need to supply an address K and then probe the output. So to read from the memory, we give it an address, and then we can just read from that address on the output. But to write to memory, so first we tell it what address we want to write to. We'll put the value on the input, and then we have to set the load bit to 1. So if we'll put a 1 on the load bit, and this is the sequential memory, so there's a clock applied here. So on the next clock edge, whatever the value is on the input will be loaded into that specific slot. So for example, address 37, and we wanted to put the value 99 in here. So this was a slot. You put the load bit high, and then when the clock signal came in, so when one of these pulses came in, the value 99 will be written into that memory slot. Now, this has already been built earlier in the Nanta Tetris course. Then we've got the screen. So the screen it's just basically a RAM chip, so 8K RAM chip with a base address of 0x4000. Now the bit contents of the screen chip is known as a screen memory map. So within this kind of memory, each bit corresponds to a single pixel on the screen, and by setting that pixel to a 1, or setting that bit to a 1, we will turn on that pixel. Setting to a bit to a 0, we'll turn off the pixel. So essentially each bit in this memory corresponds to a pixel. So by setting 1s and 0s, we can turn on specific pixels to create some patterns. Again, so this is also a built-in chip. We don't need to implement it, but essentially it is just a RAM memory element, but with a graphical user interface part to it in the CPU emulator. So we've got our memory. So this is a 8K memory, what represents the screen, so the screen memory map, and then each of these ones, correspond to specific pixels, and this is refreshed several times, and then it actually appears in here. So you'll see when you run this, you'll see that the actual pixels appear in here and so on. So this is a GUI element of the screen. And the keyboard is essentially just a single bit register that contains the ASCII code of the key that's currently being pressed. It's got a base address of 0x6000. Again, it's built in, so we don't have to implement, but again, it is essentially just a single bit register with this GUI element. So using this part of the CPU emulator, we can input keys. So when no key is being pressed, this register will contain 0, and then when you press a certain letter or a certain key on the keyboard, the particular ASCII value will appear in that register. So by reading that register, by looking at the output of it here, we can deduce which key has been pressed. So now I just want to go back to this unifying memory map. So the RAM, so this part of it is the RAM chip, the screen and the keyboard all appear together in the same memory map. So when we're writing hack programs, we don't have to worry that they're actually separate devices. We just have to worry about the specific address that we're interested in. So each part of memory has got a different address range. So the data, if you see here, so this is actually implemented in the memory.hdl chip. So this is basically just the kind of overall memory chip that integrates the RAM, the screen and the keyboard together into a single contiguous address space. So the RAM goes from 0 to 16383, which corresponds to this 16K memory chip. And the screen then, because in reality obviously the screen on it individual will also go from 0 to kind of 8K address range, but that's essentially shifted from 16384 to 24574. So that's the next 8K block of memory is what corresponds to the screen, and the keyboard is this final single register at the end. So it's got this one register at 64576. So the overall memory, it's got an input, an address, and then when we want to load things into it, so loading is actually only for the RAM and the screen. We don't load values into the keyboard, that's just the output. But all of the chips are all multiplexed together to a single output.